So now let me go to, for example, ETABS first to show you what are different types of hinges available and what input they take, right? Now you have a rough idea, so let's see that directly in ETABS also. So if you go to define in ETABS, section properties, and then you have the frame wall nonlinear hinges, and then you add a new property. Then you will first have to select whether it is a force control hinge and a deformation control hinge. So I'll directly show you what is the difference, but let me first discuss deformation control hinges. If you check that and open that list of available hinges, you will see that there is a whole list of hinges available. The last two are actually the fiber hinges. They are related to fiber modeling approach, right? So currently they are not our topic. In all other hinges, they are lumped plasticity hinges. First 6 hinges exactly, they are called uncoupled nonlinear hinges, and each of the, as the name indicates, each of the hinge actually controls that particular degree of freedom. If you go for, let's say, axial P hinge, first hinge, program will ask you to define a P versus delta relationship, axial force versus axial shortening or elongation relationship in positive and negative direction, and cyclic behavior also, everything. It will ask you to define that. And once you make such a hinge, obviously you can give this hinge some name. Once you define that relationship in axial P hinge type, you can assign that hinge, this particular hinge, to any element, to any beam or a column. By doing so, you will be telling the program that the axial force in that beam or a column versus the axial shortening in that beam or a column or elongation should follow this behavior which I give, right? It should not follow P is equal to that delta over AE, that elastic formula. It should follow my behavior, right? And I will give this kind of a relationship between P and delta, that the P versus delta should remain linear up till a certain time, but after, when the load increase from some yield capacity of that beam, it should become non-linear, and then it should go to ultimate and then go down. I will control its shape and the cyclic behavior also, right? So first we define hinges, then we assign it to different points in the program, in the model. We select a particular beam and just go to assign, here assign, and just select that hinge which we defined, right? This we can do for shear V2 type. Any cross section, beam cross section, have two cross sectional axes which is called 2 and 3 axis, right? The 1 axis is by default the longitudinal axis in all the CSI programs. If this is the beam length along that side, so 1 is by default longitudinal axis, 2 and 3 are cross sectional axis. So M2 means moment about 2 axis, M3 means moment about 3 axis, V2 V3 means shear about 2 and 3 axis, right? So if I apply, if this is a beam, let's say, with this cross section, and I apply a vertical load, the M3 will be actually the default bending moment caused by that vertical load. Let's call it as some N, let's say, because if you point your thumb towards 3, the curl of your fingers will be in the direction in which this N is going to bend your beam, right? So M3 is actually the primary bending moment caused by the applied loading. M2 will be the primary bending moment caused by the lateral loading. Since beams are mostly designed only for vertical load, therefore M3 is the primary bending moment for beams. But for columns, both M2 and M3 are the primary bending moments, because columns are designed to handle both moments, right? Similarly for beams, V2 is the primary shear force. V3 is not that primary, and we are no more interested in that particular direction for beams. So V2 and M3 are the primary actions for beams, and for columns all V2, V3, M2 and M3 all can be important. So which means that if I want to make flexural behavior non-linear for my beams, I should go for this M3 moment M3 hinge, right? Flexural nonlinearity for beams should be defined using moment M3 type hinge. If I want to define shear nonlinearity for beams, I should go for this shear V2 type, right? If I want to define torsional nonlinearity, I should go for torsion type. Axial load nonlinearity, axial type. Or in some rare cases, if I also want to define M2 direction moment nonlinearity or V3 direction shear nonlinearity, there are hinges available for that. So all 6 degrees of freedom, let me show you a larger view of the same form. All 6 degrees of freedom are here available for you. You can control or make any action versus deformation behavior nonlinear by using any of these hinges. So now it's your choice. For beams mostly M3 and V2 are used, and for columns any combination can be used. For columns there is a different case. You need to go for interacting or coupled hinges for columns, and for a reason I'll explain maybe after this slide. So the summary is that all of the 6 degrees of freedom can be controlled using action versus deformation behavior, non-linear behavior. But there are 2 types also. Uncoupled hinges, where each degree of freedom can be modified independent of the other degree of freedom. For example, if I go for a beam and define M3 hinge at both ends, M3, and by now you know that what is the input required for an M3 hinge. It is moment versus rotation. So moment in 3 direction versus rotation in 3 direction. This relationship is the input here also and on the other end also, M versus theta 3. So if I use these 2 hinges at both ends of this beam, I am not interfering with all 5 degrees of freedom which are also there at both ends, right? I am only modifying this particular M3 degree of freedom, right? So M2, V2, torsion, axial load, I am not, and M2 similarly V3, all 5 degrees of freedom or 5 other actions I am not disturbing. They will still remain elastic if I just use this M3 hinge at both ends, right? So out of 6 degrees of freedom at this end, I make 1 as nonlinear, other 5 are still elastic. They still will follow elastic formula between action and deformation. Same is the case on the right end. If I just have 1 M3 hinge, other 5 are not disturbed. Unless I also decide to include some other hinge. Let's include a V2 hinge also, maybe another point V2 hinge. Here also let's say V2 hinge. Now what is happening, that 2 out of 6 degrees of freedom are made nonlinear. This V2 will have a input equal to V2 versus let's say gamma 2, which is the shear deformation in 2 direction, a nonlinear relationship between them, right? Same is the case on the other side. So now out of 6 degree of freedom, 2 are controlled by my relationship, which are my plastic hinges, other 4 are still elastic, right? So unless you define a particular hinge or control a particular degree of freedom using that hinge, it is assumed elastic by default, right? So it's not that we need to modify all 6 degrees of freedom. Whatever nonlinearity we want to introduce, only that particular degree of freedom we will modify. For beams, we are mostly interested in flexural nonlinearity, bending moment. So only M3 hinge will be required. For coupling beams, for example, diagonally reinforced coupling beams in shear walls, we may require only a shear hinge because they will not deform in flexural action. If there is a truss element, we only may require a P axial hinge because truss element is not going to undergo bending, or we are not interested in a particular action, right? So it's not that for all elements, for all degrees of freedom we define hinges. We do it for selected elements and for selected actions only, right? But uncoupled hinges are good for example, truss elements, nonlinear truss elements or bar elements. They can be good for beams, but they may not be good for reinforced concrete columns, and that is for a particular reason. And that reason is that in columns the actions interact with each other. For example, for a beam, you know that exactly what bending moment is going to yield that particular beam, My, right? The axial load is not assumed that it is not affecting the yield moment because it is not significant in beams. For columns, you have both axial load and a bending moment, right? And they both interact to fail that particular column. So column is not failed at a particular P, it is not failed at a particular M, it is failed on a particular PM pair, right? So the actions are coupled here, they are no more uncoupled, and that's why you may not have a particular yield moment for a column only. You should always define a pair which will cause a failure in that column, right? So in beam, the degrees of freedom can be assumed uncoupled because the interaction is not significant, it is negligible. The beam is primarily bending in flexural action only, the axial load is not significant. For columns, both axial load and moment are significant, and they are interacting to have a damage in that particular column. So therefore the capacity of a column cannot be defined only by one number, it is defined by a pair, and there can be infinite different pairs which can fail a particular column. For example, a low axial load and a high bending moment will cause a failure, and also a high bending moment and high axial load and a low bending moment, right? Or any other combination in between. So there are infinite pairs of P and M which will fail that particular column. So therefore the capacity of a beam is not defined by one yield moment or yield axial load, it is defined by a complete curve which is called PM interaction curve. PM interaction curve is the capacity curve for column. It is a curve which is showing you infinite points. Each point is a failure combination for that particular column, right? So you can make it for one particular column with given inputs, amount of steel and everything, Fc prime, Fy, dimensions. You can make that curve, and that curve will be what? It will be a capacity curve. Each point on that curve is a pair of P and M which will cause failure. So now you will know that for very high P, you will require very low moment to fail that column, or for very high moment you may require only very less axial load to fail that column, right? So the summary is that for columns you may not consider degrees of freedom uncoupled. You have to use what we call as the coupled hinges to make those columns as nonlinear, because there is no fixed yield moment. In fact, there is no fixed m theta curve for column. That m theta curve depends on the level of axial load on your column. For higher axial load, your column will yield on a lower my, m theta curve will be different. For lower axial load, your yield moment will be higher, as indicated by this PM interaction curve, right? So therefore we also have hinges which take care of this coupling. interaction. So in columns you will be defining one m theta curve for your column, but at the same time you will also be defining PM interaction curve for your column. So you are telling the program that when the axial load increase, my yield moment reduce, right? Or when the axial load on my column reduce, my yield moment increase. So program handles both degrees of freedom, axial load and flexural degree of freedom, axial degree of freedom and flexural degree of freedom. It handles both degrees of freedom at the same time. If the action in one degree of freedom increase, the program reduce the capacity of other degree of freedom, right? And if the action in the other degree of freedom increase, it reduce the capacity. So this kind of hinge, which accounts for both degrees of freedom or coupling of these degrees of freedom, it is called interacting hinge or coupled hinge. Now there can be two bending moments and one axial load, right? In columns, two primary bending moments M2, M3 can be of our you can say interest, and one axial load is there. So for a three-dimensional column, let's say this is our column, and let's say these are the two cross-sectional axes. This is, let's say, 2 axes, this is 3 axes. So we have three primary actions in column, P, M2 and M3, right? So which means there can be a type of plastic hinge which will handle or which will account the interaction between these 3 degrees of freedom, right? And that should be assigned to a three-dimensional column, and that hinge is called interacting P, M2, M3 hinge, this one. Now this is a plastic hinge in which you will not only define m theta curve for one particular degree of freedom and that's all. It's not that. Here you will be defining the m theta curve for different degrees of freedom, M2 and M3 both, and at the same time you will account the effect of axial load on the shape of that m theta curve, right? So 3 degrees of freedom will be you can say modified or coupled in the same hinge. So program in this particular hinge will require you to define m theta curve in 2 direction as well as in 3 direction, and as well as the effect of axial load on those m theta curve, right? So when the axial load is more, program reduce the my in m2 or m3 direction, right? So it accounts for that interaction. It accounts for the coupling of capacity between different degrees of freedom, and then all other 3 on top are the subsets of this P, M2, M3, because they just are based on 2 out of these 3 actions. Like M2, M3 is an interacting hinge between both moments only, no effect of the axial load. PM2 is the hinge which can be assigned to a uniaxially loaded column in which the primary bending moment is M2 and you want to include the effect of axial load. PM3 hinge, this one can be given to a uniaxially loaded column in which you want have only M3 bending moment, no M2 bending moment, and you want to include the interaction with axial load. But more comprehensive is this one which I encircled. For any general 3-dimensional column, you should give this hinge. So let me write moment M3 as, let me encircle this one. This one for beams, flexural nonlinearity for beams, and this one is the flexural nonlinearity for columns, right? And since the effect of axial load is also accounted, sometimes it is called axial flexural nonlinearity, and you know already that for columns, flexure alone cannot be viewed, it is always axial flexural, because for columns axial load always interact with moment, it cannot be uncoupled with moment, right? And then you also have 2 parametric concrete and steel. Parametric simply means that it is a quick way of defining a interacting plastic hinge. For concrete it gives a template, for steel it also gives a template. So it's like instead of defining the complete m theta relationship and all that detail. You give some basic inputs and ask the program to develop that hinge for you, right? So but these two parametric options, they are only available for limited type of cross sections, right? So and last two are the fiber hinges, which we will discuss maybe next class. So now you have an overview of all the spectrum of hinges available in ETABS, right? Now the next step should be to understand the inputs required for at least these two type of hinges, which is beams and columns, and then we will go to fiber modeling in the next lecture, right? Perform 3D have far more nonlinear modeling capabilities compared to ETABS. Currently ETABS have only this, which is being shown here in this particular slide. Apart from that, we have nonlinear link elements also in ETABS, but they are not in that particular category of plastic hinges, right? They are separate nonlinear elements, although mathematically they are also like hinges, because they are also in link elements also. You can simply modify a particular degree of freedom and give your own nonlinear relationship there also. So mathematically those links and these hinges are same thing, right? It's just that they are used for different purpose and the templates to define them are named differently in this particular program. I was telling that Perform 3D have far more nonlinear capabilities compared to these ones. For example, let me give you one example and then we can end. We know that there is another kind of interaction called flexural shear interaction. When there is a flexural nonlinearity, when the beam bends and it cracks, the shear capacity of that beam reduces, right? If you define a relationship between the plastic rotation of a beam theta and the shear capacity Vn of a beam, it for low levels of theta it will remain constant, but for high levels of theta it will reduce to a very low number, because it is obvious also that when the beam is close to failure in flexure, the shear capacity is no more constant because of the reduced cross section and because of all the other flexural deformations or deteriorations, right? But this effect, that the shear capacity is reduced with increasing flexural deformation, this effect currently ETABS cannot handle. Perform allows you to actually define this kind of a curve in the form of a specific element and then put that element in your beam. The program will in that case will actually know that when that beam is bending in flexure, its shear capacity doesn't remain constant. It is going to reduce with more and more flexural deformation, right? So it may be possible that initially for low levels of flexural deformation, your shear capacity was enough against the shear demand, but at high levels of flexural deformation, your shear capacity reduce from the shear demand and your shear failure occur prior to flexural failure. This is called premature shear failure, right? Now your model, if you have this kind of a behavior input in your model, which is possible in Perform 3D, that model will be able to capture premature shear failure. ETABS will not even know this failure have occurred, right? Because it doesn't allow you to define such a detailed interaction between two actions. In this particular case, it is shear versus flexure, right? So Perform 3D allows you to define many more sophisticated interactions and behavior, nonlinear behavior, which currently ETABS may not allow. But as I have said that with more and more new versions of ETABS, many of the Perform 3D capabilities are currently being introduced in ETABS, right? So now fiber modeling and plastic hinge modeling is available, but many of the dampers and many of the special kind of elements currently are not available.